Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to the first tutorial for this week, I guess tutorial 1.1. And this homework problem was generally designed to give you a feeling for this concept of a dispersion relation. That is, what I had stressed during my regular lecture was that when you have a differential equation with constant coefficients, solutions can be written in the form of exponentials, and this leads to a dispersion relation. And first example of that would be like what I asked you in this homework problem, the part A, that is to show that if you take this, what's called the time-dependent Schrodinger equation, the one that will not be using very much. What we'll be largely be talking about in this course is about steady state transport without time variations, and much of that can be discussed using the time-independent Schrodinger equation, which is this second one here. But every once in a while, we'll actually have to go back to the time-dependent one, so it's important to be aware of the connection. And the time-dependent one is what you need if you were dealing with electrons in a potential that is time-varying. So if you had a potential that was, was not only spatially varying, but also with time. And for simplicity here, I've done this in one spatial dimension, so I've only written z. But the basic idea would work even if you had x and y. Okay? Now, supposing we have a problem where the potential does not explicitly depend on time. And a lot of what we'll be discussing in this course, as I said, is steady state, where the potential involved is not time varying. You see, then the basic rule is that as long as your differential equation, the coefficients, do not depend on time, we can always write the solution in the form of, I should write it here, in the form psi z comma t. That's the general time-dependent thing. And we can write it in the form, let me get a better pen, psi z exponential minus I e t over h bar. So this is the, as I said, because the coefficients of the differential equation do not depend on time, you can write the solution as far as the time part of it is concerned, we can write it in the form of an exponential. The z part, since the coefficients do depend on z, that is at least the way we have assumed it is, there is still this u of z. So as long as it depends on z, you cannot write the solutions to the z part in terms of exponentials. What I'll talk about next is when you have potentials that do not vary with spatially, what you can do then. Basically, even the z part can then be written in the form of exponentials. Okay. Now, again, how do you know this works? Well, as I said earlier with differential equations, there's usually not a logical way to come to this conclusion. I mean, no simple logical way, but what I can do easily is substitute it back in there and show you how it works. So the way it would be is, if I take this solution and substitute it back in there, then what happens is, let's try that. So we'll take that solution, take this off, and we are substituting it back in here. Now I have to take the partial with respect to time, and this wave function has the form of psi of z e to the power minus I e t over h bar. So the time dependence has this exponential form. What that means is when I take derivative with respect to time, that's equivalent to multiplying by this coefficient that multiplies time in this exponential. So I h bar d dt is equivalent to just I h bar times minus I e over h bar. So the derivative with respect to time just gives you this. Now you go over to this side. Okay. This is just spatial derivative, which we leave intact. And then this is u of z, leave intact. And then we put down the assumed form of our solution here, psi z e to the power minus I e t over h bar. And that should. Right. So if you assume this exponential form of the solution, put it in there, then this is what comes out automatically. Okay, so now you see I can cancel out the time-dependent, this exponential factor from both sides. And what I'm left with then is an differential equation that does not involve time anymore. So you see what I had earlier was a partial differential equation with z and t. Now I have a differential equation with just z. Right? I guess we could replace this partial derivative with a ordinary derivative. But in general, if you were keeping the other two dimensions, you'd still have x and y. And this I h bar times minus I e over h bar, as you can see, the h cancels out. I times minus I is 1. So basically, this is just E. And that, you see, is the time-independent Schrodinger equation that we'll be using by and large in this course. And as I said, just once in a while, we'll go back to that one. Okay. Now, to get to part B of this problem, in part B, what I said is, well, I guess what you saw in class, I mean in the regular lecture, is that if this potential happens to be a constant, let's say U0, then the solutions for Z can also be written in the form of exponentials. So you could write psi of Z in the form of, any constant times e to the power I k z. And if you take this solution and substitute it in here, you'd get what you call the dispersion relation for this differential equation. And this we did in the regular lecture. What happens is, I guess it's easy to see, when you substitute it in here, you get E psi 0 e to the power I k z is equal to minus h bar square over 2m. And now the point is that when I take two derivatives with respect to z, that's equivalent to multiplying by ik twice. So I put ik whole squared and then plus u0. And this whole thing then gets multiplied by the psi of z, which is psi 0 e to the power I k z. So starting from the time-independent Schrodinger equation, assuming a constant potential u0, if you assume a solution of this form, exponential, you can go back there, and now you see this will cancel out, and that will give you what we call the dispersion relation. Is equal to h bar squared over 2m. Note that I have a I squared and a minus sign, so that just all drops out. You get h bar squared k squared over 2m plus u0. And this relationship between E and K, because what it tells you is that as long as E and K are related by this, our assumed form of the solution, namely psi 0 e to the power ikz, will satisfy our differential equation as long as E and K are related by this. And note, of course, that I could not have done this if the potential were spatially varying, because then you see this wouldn't be a constant. You'd have u of z here. And then if I choose my K to satisfy this equation at one z, it won't satisfy it at another z. So the only way a solution like this would work in this form is if I'm able to choose my K such that this relation is satisfied everywhere. And that's I can only do if the U is a constant. Okay. Now you could extend this idea to do the homework problem where I said that, well, supposing someone says that the dispersion relation is not this, but has an additional term to it. Namely, let me draw a line here. So let's say we say, well, I got another term, alpha k to the power 4. Because what we did so far is, given the differential equation, how to get a dispersion relation. But often in solids, you have the reverse thing. That is, you kind of know the dispersion relation because of all the experiments that people have done on the solid. You know what mass people think it is. You know there is some non-parabolicity that you know about. And what you want to do is go the other way and figure out a differential equation that you could then use to do other problems on that solid, you see. So how would you go from here back? Well, what we can easily see is that, well, if you didn't have this term, the way you would have gone back to the original differential equation would be, instead of k, put minus I d dz. And you can see why, because d dz with exponentials amounts to multiplying with ik. And the I and the minus I then leave just k. So the basic rule would be, wherever you see a k, replace with minus I d dz. So with that principle, you'd think that this term would just give you an additional thing that would look like alpha times minus I d dz to the power 4. Whereas this term will give you minus I d dz square with h bar square over 2m. And so the differential equation corresponding to this part B of this problem would be E psi is equal to minus h bar square over 2m d2 dz2, d2 psi dz2, plus so d dz twice is d2 dz2, and minus I square is minus 1, plus alpha, and then minus I to the power 4 is actually just plus 1, and d dz fourth means d4 psi dz fourth. So this is the differential equation that would correspond to a dispersion relation of this type. So this is a principle one could use, you see, to get from a known dispersion relation or energy momentum relation, you know, h bar k is like momentum, to a differential equation. Now, there's a bit of an extension of this that's also interesting to look at, which is this part C of this problem, the last part. And that goes something like this. Supposing we have a dispersion relation that looks like this. And this is kind of relevant because, you know, in graphene, I've mentioned in part 1 that you have a linear energy momentum relationship. It looks something like V0 h bar k. And this is a two-dimensional conductor, so the k is really square root of kx square plus ky square. And so, if you, I guess I should have a V0 also here. So if you put epsilon equal to 0, then you see it becomes the graphene dispersion relation. And in graphene, there are cases actually where you actually need this epsilon also. So you might say, well, I know this dispersion relation for graphene. How would I write a corresponding effective mass equation? And here you see, if you use our prescription I just said, that, well, instead of kx, put minus I d dx. Then you run into a problem because you kind of have this square root of an operator, which is not easy to deal with. Okay? But here there is a very clever method that could be used. I believe this is the first time this was done, I think, was when Dirac wrote down his relativistic equation corresponding to the relativistic energy momentum relation. And what we're doing here is kind of a simplified version of that in 2 dimensions. So here, the way you do it is the following. instead of writing a single differential equation, you'd write what you might call a matrix differential equation. One that has two components, psi and phi. And you'd say, okay, E psi phi is equal to a matrix operator. So you have some function of, you have some differential operator here, something else here, something else here, something else here, acting on psi and phi. And so this is equivalent to two coupled differential equations. You see, it's like E psi is equal to this operator acting on psi plus this operator acting on phi. And E phi is equal to this operator acting on psi plus this operator acting on phi. Okay? And what you can do is write down an operator here such that the square of that operator is actually what you want. So let me explain this in a minute. In fact, let me just show you what that operator is. So let us say this operator, actually I'm going to write it here. This will be epsilon, this will be minus epsilon. And what you'll write here is h bar v0 times this kx minus iky, say. And h bar v0 kx plus iky. Let me. So, and this kx and ky, those would be replaced by your usual prescription. Namely, what is kx? Well, it is minus I d dx. What is ky? Well, that's like minus I d dy. Okay? Now, the thing is that this quantity has the property that if you square it, what I mean by that is, supposing I take this epsilon h bar v0 kx minus iky, h bar v0 kx plus iky, and minus epsilon, and just multiply it by itself. So this is this matrix operator. You're multiplying it by another matrix. And what you'll get is, you see, what I claim is what you'll get is, you see, if we go back to this thing, we want E to be equal to the square root of that. And so which means we want E squared to be this. And what I'll show is that if you take this operator, multiply it by itself, you basically get this quantity times an identity matrix, 2 by 2 identity matrix. So if you just multiply these two, I guess you can see you'll get epsilon squared plus this times this, which will give you epsilon squared plus h bar squared v0 squared kx squared plus ky squared. The cross terms like kx, ky will cancel out because these are the derivatives with respect to x and derivative with respect to y, which commute in the sense they can be taken in any order. So kx, ky is the same as ky, kx. Okay. So when you multiply, in the diagonal you'll get that, same here. But if you look at the off diagonal, it will be epsilon times that minus epsilon times that, you see. And so those two will just cancel out. So this will be 0 and this will be 0. So in other words, we have managed to write down a matrix operator here such that its square is equal to what we want, this epsilon, this dispersion relation we want, times I. So this is one way one can turn a dispersion relation that involves a square root. You see, the problem we had was that E was equal to the square root of that. See? So this dispersion relation that involved a square root, we could turn it into a differential equation. The only thing is, the differential equation won't be just a 2 by 2, but will be just a single differential equation, but will be two coupled differential equations. And as I said, the three-dimensional version of this is what Dirac did to write down his relativistic equation for electrons, where he actually had to use not a 2 by 2, but a 4 by 4. But the details of this, then again, I guess you can look at the solutions, but I hope you get the basic idea that I was trying to convey with this homework, namely, differential equation with constant coefficients, solutions are in the form of exponentials, gives you a dispersion relation, and given a dispersion relation, you can kind of work backwards and figure out the differential equation that goes with it. Thank you.